Just take a second and look at the air around you. It probably seems pretty calm, right? Perfectly still. But what if I told you that you're actually sitting in the middle of an invisible, chaotic storm of particles, all moving at unbelievable speeds? In this explainer, we're going to pull back the curtain and figure out just how fast that storm really is. So let's just get right to it. The big question. All those nitrogen and oxygen molecules zipping around your head this very second, just how fast are they going? I mean, are we talking like the speed of a car? Maybe a bullet? Or are we in rocket ship territory?
Well, believe it or not, the answer is hiding in one of the most fundamental ideas in all of physics. So think of this as a little investigation. We're going to use math as our magnifying glass to see a world that is in constant, furious motion all around us.
Okay, our first stop on this journey is to learn the rules of this invisible dance. You see, every gas, whether it's the air you're breathing or the stuff that makes up distant stars, is just a collection of particles in constant, random motion. They're bouncing off each other, off the walls, and even off you, billions and billions of times every single second. And this dance, it isn't total chaos. It actually follows a specific set of rules. We call it the ideal gas law. This equation is our starting point. It's this beautiful link between the big things we can actually see and measure, like pressure, volume, and temperature, and that tiny, microscopic world of dancing particles. This is the language we need to speak to solve our mystery. So, with the rulebook in hand, we can finally get to the real challenge. How in the world do you measure the speed of all this molecular chaos? And here's where it gets a little tricky. See, not every molecule is moving at the same speed. It's kind of like a swarm of bees, you know? Some are darting around like crazy, others are moving a bit slower. They're all going in different directions. So what does the speed of the gas even mean? We need to figure out a typical speed. Now, your first thought might be, well, let's just take a simple average. And that makes sense. Let's imagine we've got 5 molecules moving at 1, 2, 3, 4, and 5 meters per second. We add them up, divide by 5, and boom, 3 meters per second. It's a decent start, but in physics, especially when we're talking about energy, there's a much, much better way to do it. And that more powerful tool is called the root mean square speed, or RMS speed for short. The reason this is so important is that this special kind of average is directly tied to the kinetic energy of the gas, how much oomph all those particles actually have. Now, it sounds complicated, I know, but trust me, it's just 3 easy steps. The name literally tells you what to do, but backwards. First, you square all the individual speeds, then you find the mean, that's just the average, of all those squared numbers, and finally, you take the square root of that result. See? Square, mean, root. That's all there is to it. So for our 5 little molecules, the RMS speed turns out to be the square root of 11, which is about 3.32 meters per second. You'll notice it's a little bit higher than our simple average of 3. And that's the point. This method gives more weight to the faster particles. And since kinetic energy goes up with the square of speed, those faster particles are carrying way more energy. For a physicist, this is the number that really tells the story. And all of this leads us to the master formula. The best part is we don't have to go and measure every single molecule. Instead, we can calculate the RMS speed directly if we know just 2 simple things: the absolute temperature, T, and the mass of a single molecule, M. This formula right here is the key that's going to unlock everything else for us. So now that we have that key, let's explore one of its most amazing consequences. It turns out that temperature isn't really just about hot and cold. It's literally the speed dial for the entire molecular world. So that begs a simple question, right? If we crank up the heat, what happens to the speed of these molecules? If we, say, double the temperature, does the speed also double? Let's find out. Okay, check this out. This chart shows something really interesting. Notice that when we crank the absolute temperature up by a factor of 4, so we go from 300 Kelvin to 1200 Kelvin, the RMS speed only doubles. So what that tells us is it's not a simple one-to-one relationship. Because of that little square root in our master formula, to get the molecules moving twice as fast, you actually have to pump in 4 times the amount of thermal energy. All right, we've built our toolkit. We understand RMS speed. We get how it connects to temperature. So now let's use it to answer a really, really big question. Why does Earth have an atmosphere at all? I mean, why hasn't all the air just floated off into space by now?
This number is the entire reason, 11,200 meters per second. That is Earth's escape velocity. It's the speed that anything, a rocket, a baseball, or even a tiny little air molecule, has to reach to break free from Earth's gravity and just never come back. And this brings us to our final investigation. We know the mass of an oxygen molecule, and we know the speed limit it needs to break. So let's take our master formula, work it backwards, and calculate the exact temperature our planet would need to hit for a typical oxygen molecule to escape forever. And there's our answer. Whoa, 83,600 Kelvin. That is an absolutely insane temperature. We're talking more than 14 times hotter than the surface of the sun. Our planet's atmosphere is never, ever, ever going to get that hot. And that is why our oxygen is safely stuck here, held in place by gravity. You know, this also explains another cool mystery. Why is our atmosphere made of heavier gases like oxygen and nitrogen, and not lighter stuff like hydrogen? Well, it all goes back to our formula. See how mass is in the denominator? That means at the very same temperature, lighter molecules move way, way faster. Hydrogen is so light that over billions of years, a lot of it has actually reached escape velocity and drifted away, leaving all the heavier, slower gases behind. And that brings us to one last thing to chew on. The atmosphere on Mars is mostly carbon dioxide, which is even heavier than the oxygen in our air. So are its molecules moving faster or slower than ours? And keeping in mind that Mars is colder and has weaker gravity, what does everything we just learned tell you about its ability to hang on to its atmosphere, both in the past and in the future? Something to think about.